Thanks, John. Thank you all. I think you'll agree the agenda for today looks really exciting, so we'll hopefully kick this off in the right direction. My name's Neil White, co-presenting today with my friend and colleague Rod Chapman. We both work for Altran. 45,000 engineers across the globe. Altran is almost certainly one of the largest engineering multinationals you've never heard of, and that's fundamentally because we're a business-to-business company rather than a business-to-consumer company. Okay. Piece of Altran that I run exists for one reason and one reason only. Okay? We exist to write software correctly, okay? Which is a fairly arrogant statement, I appreciate. We fundamentally exist to write ultra-low defect software. That's all we want to do. Stretch target, 0 defects. We're not quite there, but ultra-low defect software for sure. Okay? As a side effect of that, we want to push up what the software industry considers acceptable for defect levels. Okay? No other mature engineering industry, mechanical engineering, electrical engineering, civil engineering, allows the level of defects that the software industry seems to think is acceptable. And to us, we genuinely believe with a passion that that's just not correct. Okay? I'm not standing here worrying that the floor is going to collapse underneath me because a structural engineer didn't do their job properly. Okay? And yet people go, oh, turn it off and on again, that's okay, it's software. All right? To us, that isn't offensive to us as engineers. So we strive for ultra-low defect software. Okay? Fundamentally, we'll operate anywhere. We're not tied to one industry, we're not tied to one product. Frankly, I'll work for anybody who'll pay me. We find ourselves a lot in places like air traffic control, railway signalling, and that kind of area. The schematic of air traffic control, this is the UK, little areas. Each of those little coloured blobs gets a team of controllers looking after the aircraft in that airspace. Quick show of hands, how many people have flown in or out of the UK airspace in the last 5 or 6 years? Quite a lot. Okay, so good news. I personally signed the safety certificate for rolling software out into UK airspace and UK air traffic control. Okay? The software is built with the technologies that Rod's going to talk about in a minute. Okay? You've all entrusted your life to it already, which means you already trust me and this software. All right? That means you're not a hostile audience. Okay? So this is going to be great, right? I'm going to do a little bit of scene setting into the rationale and the why that's behind the ultra-low defect concepts. Rod is then going to dive hardcore into some of the technology and look in particular at Spark, which is a programming system that we use to generate some of this stuff. And then as long as he doesn't overrun and I get some time at the end, I'm going to go through some real-world examples and talk about the way this is used in places that maybe, you know, if you stop and think, software's obviously there, but you haven't thought about it in the past. So, this story comes from a piece of UK infrastructure. Essential UK infrastructure. I'm not going to tell you exactly what it is because I quite like my freedom and liberty, to be honest. Piece of essential UK infrastructure, you imagine a room with lots of people, with lots of screens, they're all working away, they're all using the same piece of software. Okay? One of those bits of software, and I'm not going to tell you who wrote it, it's a company you'll know of, but it would be unfair to name them because they're not here, but it's not ours, for sure. One of those bits of software had an array buried down somewhere in the bottom of it, yeah? And they were accessing the array, and this is all kind of good kind of stuff, right? It's all going very nicely. Then it did this. Okay? And around the room, lots of people sitting at screens. The screens went boom, 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 boom. Okay? Piece of critical national infrastructure. So the next day, it was being discussed in Parliament. How did this happen? What went wrong? Okay? Set up a public inquiry. That public inquiry called in the software vendor, software manufacturer, and every other software vendor that also provides software into the same kind of system. And they stand there and they say, have you tested for this? Are you confident that your software will never do this? Okay. So I pointed out to them that this particular piece of software, not ours, I'm going to say that a couple of times, this particular piece of software had been in service for 10 years. It had been running 24/7 for 10 years and it had never done this before. Do you honestly think a few more tests are going to identify this problem? You cannot rely on test for critical functions in complex systems. And by critical, I just mean, you cannot rely on test in complex systems and the type of systems we're building nowadays. Okay? And then I did answer the question, because if you're in a public inquiry, top tip, answer the question. Okay? Have we tested for this? No. Not at all. None. Am I confident our software won't do this? Absolutely confident our software won't do this. All right? Then there was a bit of a pause. They processed that. And then someone said, you better explain. Okay? And it's really easy. Okay? A lot of programming languages and programming techniques will allow you to push pointers past the end of buffers. They rely on the coder, the programmer, to make sure it doesn't happen, or they rely on code review to check it's not going to happen. we use programming techniques that do not allow it to happen. We move that responsibility from the coder to the language. That leaves the coder doing what they're best at, which is designing really complicated algorithms that computers can't do. And it leaves the computer doing what it's best at, which is checking really basic stuff, okay, that people, you, me, definitely me, are not good at doing either, right? Because I want to be designing algorithms, not checking for buffer overflows, okay? The programming system we use does not allow this to happen. Therefore, no, I haven't tested for it at all. And I'm really confident it's not going to happen. By design, it can't happen, okay? Which led to a really bunch of interesting conversations about other people do other things. So, Roddy's going to talk a little bit now about how we go around that with some of the technologies, and I'll come back later and give you some examples.
Okay. Thanks, Neil. So, audio okay? I'm on. So, this programming system we have called Spark, I'm going to open up by telling you what it is. I will tell you what it isn't, because it's very commonly confused with other things. And then we'll get a bit techie about how does it actually work. And I warn you, there will be some mathematics. So please don't be scared and run away. We've locked you in, don't worry. So Spark is a programming language. Oh, big deal. It's a third-generation imperative programming language. For the older members of the room, it looks a lot like Pascal. For the hardware engineers, it looks a lot like VHDL as well, which is not a fluke. It is specifically designed for what we would call low-level or bare metal or ring-naught programming. So systems where we have no operating system, no COTS, we don't have no Windows, no Linux. We are literally down on Intel, what you would call ring-naught or supervisor mode, or, you know, we're at the bare metal kind of programming, the microprocessor level, because a lot of our customers don't like operating systems. They're not reliable enough and they're not trustworthy. So it's similar in scope and ambition to say C or C++ in those application areas. But also, it's not just a language. There's a bunch of technology goes with it. There are tools that go with the language, like compilers, but also what we call static verification tools, and I'll talk about that in a second. The tools and the language go hand in hand. You can't have one without the other. The tools are useless unless you're actually using the programming language in that form. And you can't claim to be using the programming language unless the tools actually verify that you're doing it right. You can't do this by hand or by review, code review or anything. More importantly, though, when you get used to it and you've used it for a little while, you notice that the way you think about designing programs changes. When I write Spark, I know there's going to be this pesky tool to check up on me. So the way I think about designing code is different with Spark than it is in C or whatever other language I might be using. So it becomes a set of disciplines for software engineering, and it changes the way we do code review. It changes the way we do test as well. So all of the surrounding processes have to be adjusted, and that's really, really important, because hopefully it's a good thing. It is all of the above, is the point I want to make. It's not just one of those things. What it isn't, well, it isn't that. Again, older members of the audience, I'm looking at Roger, I don't know why, but older members of the audience will remember an instruction set called Spark with a C on the end. It's not very popular these days. You'll find it in two places. If you look at the top 500 supercomputers in the world, 6 of them have that. I checked the other day. 6 of them have this instruction set in. The other place you'll find it mostly is in orbit around the Earth and on Mars, because it's the go-to instruction set for spaceborne applications, particularly the European Space Agency, because you can buy these radiation hard. It's just a fluke of history that this became the machine you needed for satellites and stuff. It is also not that. If you're expecting me to talk about Hadoop and big data and Apache Spark, sorry, you're in the wrong talk. But you're stuck here now, so please stick around. You might learn something. So it's not Apache Spark. I have to turn a lot of people away from our LinkedIn group who are Hadoop developers, and I'm like, no, this isn't the right group. Go away. So we're not that either. But it's not. I should say we were here first. We've been using this name since 1987. Or something like that. So we have the moral high ground, if not the trademark. There's a debate over who actually has the trademark anyway. So what is this static verification idea? Well, basically, it's not dynamic. If dynamic verification is this idea of, you build something and you run it and you observe it and you see if it works. That's dynamic, because you're sort of running and observing. Well, that's called testing, right? Well, it ain't that. Static verification is analysis of design artifacts. And I say design artifacts because it doesn't just mean code. It could be designs, it could be English text, it could be models like UML or MATLAB Simulink models or notation called SCADE. Running your spell checker on a Word document is a form of static analysis of your written text, because all the computer does is it looks at each word and says, is it in this dictionary, yes or no? Nice and simple, right? So it's analysis without running. And that includes human activity. So the basic idea of doing code reviews, either inspecting your own work or getting a peer, maybe a peer review. Pair programming, which is a common practice from XP. Pair programming is a form of static analysis because there's someone else next to you going, whoops, you've made a mistake. That's a static analysis engine. It just happens to be in someone's brain. So human activities count as static analysis, but we're really interested in what we can do with computers. I really want to know what I can do with a tool running on a computer to do this work for me, because computers are fast and available, and you can buy lots of them for no money, basically, because CPU cycles and RAM chips are cheap, right? Okay, so why bother? Well, this kind of analysis can prevent defect classes. We can make it, as Neil said, we can make it impossible to have certain types of bug in our software. They're just not there. You can't express some bugs in Spark. So good. Say that's a good thing. Any defects that do remain, well, you can find them sooner. You can find them now by static analysis, or you can find them in 6 months' time by testing, or in a year's time when some customer reports a bug, but you've already shipped 1 million systems. Well, go figure which one's cheaper and easier, and when you're going to be able to fix that. This saves money, clearly. Fixing bugs sooner is usually cheaper, and that's sort of software engineering economics 101. And also what we can, if you really get confident with this, we can eliminate or improve later verification activities. So if I can prove statically, using maths, that my system, as Neil said, doesn't have any buffer overflows in, well, why would I bother unit testing for buffer overflows? Maybe I'll just get so confident that I just won't do that level of unit testing at all. So on a lot of the software that Neil talks about, we don't do unit testing anymore because it ain't worth it, because the static analysis is so strong, we don't bother with the unit testing. And that means I take all my unit testing team and I say, hey, you guys can be developers, guys and girls. Go and be developers instead. And they like that. It's better for the team. We get more productivity. So this is good stuff. So what would I like from a static analysis tool? Well, seeing as it's Christmas, I say, dear Santa, I want a tool which is firstly said to be sound. Now, I have to define what this means. It depends on what question you're asking. So if I'm asking a tool, are there any bugs in my program? Okay, that's the question I'm asking. And the tool says, no, I can't find any bugs, but it's lying to me. That is a false negative. It's a negative answer because it said no, but it's wrong. So false negative is the worst case thing that can happen, because then I think, oh, my system's great, no bugs, and I ship 1 million copies into the field, but there are critical bugs, and it's just failed to find them. A tool which has no false negatives is said to be sound. This comes from the mathematics community, because a proof is said to be sound. The flip side of this is complete. This is the flip side. The false positive is when you say, are there any bugs? And the tool says, warning, there might be a bug on line 10. Warning, there might be a bug on line 11, and so on and so on. And it says, there might be a bug, but I'm not sure. And you go, oh, this is really annoying. So the false positive is it saying there is a bug, but actually there isn't. That's really annoying for me, because then I, using my poor human brain, have to go and check to see if these really are bugs or whether they're false positives. And then I have to wave my arms and try and justify why it's not really a bug. Really annoying. The number one source of complaints for all static analysis tools in the world is there are too many false positives. It's unfortunately a fact of life. It's called completeness because of a guy called Kurt Gödel and another bloke called Rice. Ask me in the bar about Gödel and Rice later. I want a tool which is deep. I want a tool that's not just a spell checker. Spell checking English is what I would call a trivial static analysis. It's just look it up in a dictionary, yes or no. Easy peasy, right? Hard problems are things like, does my code have any buffer overflows in? Does my code terminate? That's a hard one. You've all probably heard of Turing and the halting problem, right? Some of you have, I guess. So yeah, do my loops terminate so that my program doesn't just drop into an infinite loop and appear to do nothing? That's a hard problem. So I want deep problems. I want it fast. I want a tool that will tell me I've made a mistake now, before my hand comes off the keyboard. I want a tool to go, no, you've done it wrong, because then my concentration is still going strong. There are only 4 timescales that matter. There's now, coffee break, lunchtime, and overnight. Yeah, overnight's what you can do on your Jenkins server on the whole system. Anything more than overnight, people won't use it. But what I want is now, which is really important. And I want what's called modularity. This is about being able to do the analysis on incomplete programs while I'm building them. I don't want to have to wait till I got the whole program in quotes, because I have to wait for the whole program. Again, I won't do it, and it's too slow. If you have to do whole program analysis, it's typically too slow. It tends to explode. So this modularity is to do with making the analysis both parallel and therefore very, very fast, and that matters. So easy, huh? Unfortunately, Santa writes back and says, go away, you can have about 3 and a bit of those goals, and you don't get to choose, some tool vendor chooses for you. So whoever wrote Pylint, or QAC, or Clockwork, or Coverity, or any of these tools, they choose. The tool vendor decides which goals you get, and you don't get much say in the matter. And the incentive on the tool vendor is not aligned with your incentive as a developer of critical software, which is a bit of a problem. Why is it so hard? The simple answer is ambiguity. The languages that we use to program computers are horrendously ambiguous. And this may be a surprise to some of you, because surely you type some code in, right, and you know what it means. No, you don't. Alan Turing said this in 1947. He said you have to use precise languages or trouble is bound to result. And he was right. And programming language design went the wrong way for the next 40 years. The languages we use are ambiguous. And if they're ambiguous, you don't know what they mean, how is a computer going to check your code if you don't know what it means? This is bad. So who knows C? Come on, there must be a few still people who will admit to programming in C. Okay, there'll be a quiz. So what does that line of code there mean? Given a couple of variables, I and A, what does that mean? Has anyone got the guts to give me a semantics for that line of code?
Probably depends on which compiler.
Mostly correct answer. Sitting on the fence, very good.
On the right-hand side, if you've got an array and you increment it by 1 to give you an index, and you assign the value to variable I on the left.
Nah. Anyone else here? Okay, this could go on all day. One more. Eh? Thank you very much. No one normally gets that. Yeah, the correct and only answer you can give is that this is an undefined behavior, which means all bets are off, you've no idea what it means, and the compiler can do anything it likes with that line of code, including make random assumptions and then optimize the rest of your program based on completely wrong and arbitrary assumptions, and all sorts of wacky stuff happens. So this is the source of, this is called an undefined behavior. Because there's 2 side effects to the same object and only one's a semicolon, basically. That's undefined. And C90 has 107 of these, right? So do you know what they all are? Every single one. And do you know how to avoid? No, of course you don't. So what can we do with static analysis? Well, what I would call first base is basic hygiene. So things like don't use the goto statement. That's easy, right? That's trivial. Things like coding style, you should all have some, definitely. And you should get a tool that enforces some style. Things like having the compiler warning switched on and don't have any warnings. That's a basic discipline. Second base, what I would call dumb bugs. So this is stuff like the uninitialized variables problem. That's an undefined behavior in most of the languages we use these days. And things like so-called code smells or defect attractors. Things like in C, saying if A is assigned to B, then, did you really mean assignment or did you mean equality because you forgot to type that extra equal symbol? Did you say equal or equals in your if statement? So these things which are usually wrong, so-called code smells, you can spot fairly easily and trivially in most languages. Third base gets interesting. We get to what I would call the deep implicit rules. So these are things that you should never have in any program, but they're hard problems to solve. Things like buffer overflow, arithmetic overflow and underflow is particularly difficult to deal with and is undefined in C and C, or signed integer overflows in C and C++ are undefined, which is really annoying. And just all of these undefined behaviors are appallingly difficult. Some of them are really hard to get rid of in some languages. So this stuff is hard to do. Fourth base is where the fun really starts. This is where I want to verify stuff about my application running in its environment in the outside world. So in a system called Tokeneer, there's a correctness property that I think it's something like if the door is open and the guard is not present, then the alarm is ringing. That's nothing to do with C or C++. That's not a programming language thing. That's a God forbid, a requirement. That's an actual security property of my application. Can I prove that about code? That's where we get to writing assertions and so-called contracts in the language and being able to prove really interesting, difficult things about software. The hard bit about that is that you have to think about it, which I know might be a challenge for some software engineers. You have to actually think about what you want in your code to be true, And you have to design the code to be like that. And that requires some actual brain power. So Spark is weird. It gets to fourth base through the use of things like contracts. And about 4.9 of the goals. And I said we only get 3.5 for most languages. How do we get to 4.9? The missing 0.1, by the way, is the false positives problem. 0 false positives is impossible because of Gödel's incompleteness problem, blah, blah. How do we do it? So the main tricks, we use a subsetting. So we get rid of tough language features that we can't analyze. So, uncontrolled concurrency is the elephant in the room of programming language design. It's so difficult to get concurrent programming right that we have to radically subset what we can do with tasks and threads in the language, and so on. And we have contracts. So those of you who come from contracts from languages like Eiffel, C#, Java has a thing called JML, contract language. We have contracts in the language to make the modularity thing work properly, to tell us what we need to know, where we need to know it in the language, and that's super cool. If you haven't come across contracts in programming, you should find out about it. So this is basically how we cheated and got the language to work. So a very techie bit is an example of some verification. This is a real story from a real bit of code that I wrote. I implemented something called skein. Skein is a cryptographic hash function. It was one of the contenders to be SHA-3. It lost. It was one of the final 5 in the competition to become SHA-3. It didn't become SHA-3, another algorithm won. Skein was one of the contenders, and I thought, oh, this would be a laugh. Let's implement it in Spark and see if I can verify some correctness properties of it. So I did. And one of the properties of Skein is that the user, the caller, when you initialize the algorithm, you tell it how many bits of output you want. So it's a variable length result. You can say, I want a hash that's 128 bits or something, and you get that many bits out of the algorithm. So you tell it this hash bit len. And then the finalization algorithm, when you throw data at it and it hashes it, and then at the end you say, okay, give me the answer. And there's this finalization algorithm that goes around generating blocks of data for you until you've got the number of bits you asked for. Right, easy, huh? So the specification of Skein, the mathematical specification, says that you take the hash bit length, divide by 8, and then you do this funny looking operator. That's an integer ceiling operator. And that gives you the number of bytes. So it's rounding up to the nearest byte for the number of bytes of hash that you get based on the number of bits that you asked for. Fine. So the reference implementation designed by the people that designed this code, this is written in C, it looks like this. It says you take hash bit len, and to do the rounding up, the ceiling operator, you add 7 and right shift 3 bits, which is right shift 3 is divide by 8, right? So you add 7 and divide by 8, and that gets you the ceiling byte count based on the number of bits, right? And then you loop, you go round and round and round, generating blocks of output, and each block you copy into the buffer that's supplied by the caller, and everything's fine. So I translated this into Spark and did the stuff. Now the data flow, we have something in Spark called data flow analysis. This reminds me that the loop has to execute at least once, because executing that final loop 0 times would be bad, right? And Spark is sensible enough to say, well, you've got to execute that loop at least once. Therefore, this byte count variable must be at least 1. Seems reasonable, right? Therefore, I use the type system in Spark, and I say my output byte count type is a U64, but it must be at least 1 up to a very big number divided by 8 plus 1, which is the number of blocks I can get, or the number of bytes I can get, sorry. It's the number of bits divided by 8 and rounded up. But it's got to be at least 1, and then I give myself a byte, and I use the same essential assignment. I say that byte count is hash bit len plus 7 divided by 8. Easy, huh? Well, okay, the static analysis tool comes in, and it does this thing called VC, verification condition generation and theorem proving, and it generates a conjecture, this is the mathematical bit, right? A conjecture that basically says, if this assignment is going to work, the value of this expression must be at least 1. Otherwise, I've blown this type, and that's a type violation. So I get a verification condition that says, if hash bit len is in the range 1 to 2 to the 64 minus 1, can I imply, that's an implication operator, that hash bit len plus 7 mod 2 to the 64 divided by 8 is at least 1. Now, with a moment of reflection, you might look at that and go, not sure that's true. Does it look true? Is it not true? If you throw this at an automated theorem proving tool, we don't do this by hand, obviously. We have theorem proving engines that do this. If you throw this at a theorem proving tool like Z3 or CVC4 or one of the contemporary tools, you get this result. And you think, oh, shit. This is what happened when I wrote this code. Theorem prover said no. I was like, ooh. Well, if you throw it at a really modern theorem prover, you get a better answer. It comes back and it says, counterexample, when hash bit len is 2 to the 64 minus 7. So if I put, for example, 2 to the 64 minus 7 in here, well, 2 to the 64 minus 7 plus 7 is 2 to the 64. Mod 2 to the 64 is 0. Divided by 8 is 0, which is not greater than or equal to 1. Oh, crap. And that loop could go 0 times. So the problem here is this modulo n plus. The plus 7 is a modulo 2 to the 64 plus 7, and it can overflow and get you back round to 0. Oh, crap. Horrible corner case bug. The theorem provers are awesome at spotting corner cases that you would never think of. It's what they do. So in Spark, we just restrict the range of hash bit len to exclude the largest 7 values. So types are cool. In the C code, that the designers actually submitted to NIST and NSA for evaluation, this bug is there. So if you do ask for 2 to the 64 minus 7 bits, byte count is 0, the loop executes 0 times, and you get back a pointer to an undefined block of memory that's never been written to, which might look like a perfectly valid hash function result, only you might get back the same undefined block of memory every time you call it, which is bad for a hash function. You're not supposed to get back the same answer every time. So it's a goof on the part of these people who are supposed to be competent cryptographers, but they still can't get C code to work properly. The theorem prover is amazing at spotting this stuff. It's just uncanny what it can find. So that's the techie bit. Whew. Neil, you're on.
Thank you. Oh, I'm a bit short. Okay, let's speed this up. Right, this is the bit where I have to remember I don't have a mic and I can't go walking around and pointing. Okay, so I'm just going to whip through a couple of examples where we've used this technology or other companies have used this technology and give you a bit of insight into some of the uses. Doesn't take a rocket scientist to spot landing that helicopter on the back of that ship is not too bad size-wise when the sea's flat. It gets harder and harder as the waves get bigger and bigger, fundamentally. We built a landing system that basically guides that helicopter into the back of that frigate, particularly in rough seas. Okay? Fundamental reason is you can pretty much get a helicopter off a frigate in any conditions. Right? You give it some welly and off it goes. Okay? If you're trundling off to do air sea rescue and pull people out of a sinking trawler, it's considered very bad form in the air sea rescue business to rescue them from a trawler, come back and crash the helicopter. Okay? Seas are measured in things called sea states, right? This enables a helicopter to get back. Basically, you don't go unless you know you can get back. And this enables a helicopter to get back in worse sea conditions than it otherwise could. It's a really good example because you can actually count the number of rescues that were done that they wouldn't have been able to take off if they knew they couldn't get back. You can actually count the number of people whose lives were saved. Not by the software, frankly, they were saved by really, really brave aircraft crew, but the software contributed to getting those people back, which is great. So this system's been in operation for 20 years. Okay? We've had one bug reported. Okay? I quite like that one, because for a lot of years I had to stand here and say, this system's been in operation for 10 years, we've had no bugs reported, and nobody believed me, right? Now it's 20 years and one bug, it's a slightly more credible story. Okay? Rolls-Royce, so I started talking about aircraft, lots of people fly, Rolls-Royce jet engines. Okay, there's fundamentally two boxes of electronics in a Rolls-Royce jet engine. There's one which is what they call a full authority digital engine controller, right? That's the bit that controls the thrust and all the rest of it and drives the engine along. Rolls-Royce write that, and they do it in Spark, okay? The second box in there is an engine monitor, okay? We write that, and we do it in Spark as well. The engine monitor sits there looking at pressures and temperatures and that kind of thing across the engine, carefully works out things like harmonics of vibrations and that kind of thing, and it can tell you if it sees a particular vibration harmonic, it knows that actually it's that bearing wearing just there, and it can tell the airframe owner, right? It's really good for a number of reasons. First off, safety, right? You can do your maintenance before anything goes wrong because you can spot these things wearing out, which is good for safety. Funnily enough, it's good for reliability. Okay, so at the moment, what they do is they strip aircraft engines down based on flying hours. Have a look at them, decide they're fine, put them back together. Okay. There's a rule that says if it ain't broke, don't fix it. Doing that, pulling them apart and putting them back together has a nasty habit of breaking some of them, thus reducing the reliability. Okay? So it actually increases reliability by not taking apart perfectly good engines. And thirdly, if you're only taking things apart when you really need to, it's cheaper, right? So it's a really, really nice harmony of safer, more reliable, and cheaper. Okay, so I won't ask for show of hands, but I'm guessing most of us have a credit card. modern credit card encryption works on a public-private key infrastructure. Your credit card has a public key, okay? And the private key is stored in a vault somewhere that I'm not allowed to tell you where it is, okay? So Spark was used by the manufacturers of that to build the system that actually generates the public-private key pair for each credit card, validates that it's a strong key, lets the public key out, but doesn't let the private key out. That last bit's quite important, okay? And even more important is the master private key doesn't get out and all this kind of stuff. Again, it's been in operation for about a decade. 0.04 defects per 1,000 lines of code. Okay? That's low. This is a system, I like this one. So this is a system we're doing for Network Rail at the moment. Alongside Network Rail, we've built them effectively a prototype backup signalling system. Okay, so the trains run great. I've got a train here today. It was perfectly on time. But when the signalling system goes wrong, everything grinds to a halt. Right? It genuinely requires people with flags to go out onto the track and start waving flags to get the trains moving again. What Network Rail said to us is, we know how much that costs us. If you can build a backup signalling system for less than what it costs us to get people out there with flags and the penalties that we have to pay, go for it. Okay? So we've built them a prototype. When I say prototype, it's installed on a real train running on real track, but only one or two to show it works. Blending all sorts of low integrity data like GPS and mobile phone signals, blending those low integrity sources together to give us a single high integrity source that's good enough for controlling trains, right? Which is a pretty radical solution. We're pretty hopeful that they'll take this forwards and we'll move on to a proper deployment. Rod mentioned Tokeneer earlier. I stuck this one in here simply because you can go and look at it. Tokeneer was a program we did for the American NSA, National Security Agency. Okay, they'd heard about the kind of tools we were using, and they came to us and said, "I would really like to see you use your tools on one of our systems, so we can see if we can reduce the defects in our security systems." But we're American, so we're not going to tell you anything about any of our systems. Okay, so they funded us to do what is effectively a demonstration. Okay, so we built a system that controls access to a secure area, basically a door control system. Built it using all of our tools technologies. Great, they loved it. Went on and did a whole bunch of things internally with it. But we also said to them, well, hang on a minute, it's not a real system, right? It's a demonstrator. Why not release it? And yeah, it's of no cost to you. So we actually managed to persuade the NSA to release the entire project set, documentation, code, the whole lot, under a permissive license, right? Which is kind of bizarre when you think about what they do for a living and just how little they tell you. I mean, they won't even tell you what their phone number is, but we managed to persuade them to release all of this. So actually, it's hosted by Adacor, who are the commercial tool vendors for Spark Technologies. On Adacor's website, you can actually go and download a significant size project with all of the code and all of the design documents and everything else, and have a play with this kind of stuff. Been particularly good for the research community and university community because it gives them a proper commercial product to go and look at rather than playing with their tools on noddy things. So that's really helpful. Well, I started with air traffic control, so I'll finish with air traffic control and dive a little bit deeper into this one. We saw this picture earlier. This is our sort of schematic of UK airspace. And there's a bunch of controllers. Each little coloured area has a team of controllers looking after the aircraft in there. Okay, they look a bit like that. Okay, this is a really old picture. All right, in that particular picture, they're staring at a radar screen. Okay, the information they get tells them where the aircraft are right now. Okay, you can see where they are right now, but it tells you nothing else really. It's just a bunch of right now information. They have to work out in their head what's going to go on in that airspace over the next time, and what do they do with the aircraft to make sure they keep them all apart. Fundamentally, that's what limited their abilities, is working out what's going to happen in the future. So we built them a system which is fundamentally designed to look into the future and predict the future. We take that information about the what now, we take the radar tracks and know where aircraft are now, but we also factor in their flight plans, the instructions they've been given to climb and descend. We look at the weather, okay? We look at what aircraft it is. So a little Cessna aircraft gets blown off course far more easily than an airliner, okay? But actually a 747 gets blown off course more than a small airliner. We factor all of that in. What type of aircraft is it? What does the weather look like? What's it been told to do? What's going on? How stroppy is the pilot? And we produce these predictions. Oh, you laugh. Some of them are, God. You really upset an air traffic controller, right? You really upset an air traffic controller, they send airliners out over the North Sea on a loop just to calm down, right? Watch them do it. We build a model of what we think is going to happen to that aircraft over time. So I don't particularly like this diagram because it makes it look like it's all kind of the uncertainty. We build a model of where I think it's going to be with the uncertainty, the probabilistic uncertainty of where that aircraft will be. This makes it look like the uncertainty just grows over time. It's way more complicated than that because certain maneuvers actually bring the uncertainty back in. If you tell an aircraft to climb to a certain level, it's quite good at doing that, and your vertical uncertainty drops quite a lot. So actually the uncertainty is more like a sausage in multiple dimensions going forwards. Once we've got all these aircraft positions, we can start doing some really quite complicated analysis and algorithms around them about what the entire airspace looks like over the UK for the next quarter of an hour. The key thing with that, though, is although they're incredibly complicated algorithms, the really important thing is we present the answers to the controllers in a really simple, easy to comprehend way. Because the last thing you want to do in an emergency situation is go, here's loads of really complicated data, right? So we put a lot of effort into then putting that information in front of the controllers in really straightforward ways. This is fundamentally a graph, right? So along the bottom you've got time, I can't jump around. Along the bottom you've got time, and up the top you've got distance, okay? And each of these little icons on there represents 2 aircraft, not 1, but 2 aircraft, okay? And what it tells you is so if we pick this one, for example, what it tells you is, in about 9 minutes' time, these aircraft are going to be 12 miles apart, okay? Slightly strange, why did I pick 9 minutes' time? Well, the short answer is that's the closest they ever get, okay? I don't know how far apart they are now, but I don't really care. I just know it's more than 12 miles, is that what I said? 12 miles? And I know they're not going to get any further. So it lets me look at how close they're going to get at their closest point of approach. So fundamentally, if I can manage all my traffic up here, right, a long time in the future, they're going to be a long way away. That's good, all right? That's coffee break time, all right? If I'm down here, very soon they're going to be very, very close together. That's not so good, all right? It lets the controllers see at a glance what their picture of their airspace looks like, and then if they want to, they can process more information. So, for example, the shape gives you a bit of information. That one that looks like a fast-forward symbol, for those that remember cassettes, okay? That's 2 aircraft that are catching each other up. So the one behind is obviously catching very slowly. Could well be that it's only 12.5 miles apart now. It's just catching very slowly, yeah? The one that looks more like a bow tie, have I got a bow tie? Yes, I've got one down there. All right, that's 2 aircraft that are coming towards each other head-on, okay? So in a couple of minutes, well, is it 11 minutes' time, they're going to be 4 miles apart. They may well be 250 miles apart right now, but if they're approaching head-on, they're closing their speed. But what I'm really interested in is how close they get, yeah? So we enable the controllers to take the output of some really quite complicated algorithmic work using an awful lot of input data, but see very simply and very straightforwardly what they need to do and what they need to talk about. Almost all of that system's written in Spark, okay? Say almost all. Okay, so almost all, as you might have noticed, the little bit of HMI is written in antiquated X windows to make it look the same as all the other tools they've got, not different. But all of the really important algorithmic bits written in Spark. It's about 250,000 logical lines of code. Okay, I hate counting lines of code, but logical lines of code, so no spaces, no commas, no annotations. If you split your if statement over 3 lines, it's 1. All of it is proven type and memory safe. Okay, so for any input data, for any state we get into, there is no undefined behavior. Right? The system will not crash. It will not raise an exception. We have to handle bad data, right? We can get into states where we go, hang on a minute, this looks bad, and this input doesn't make any sense compared to that input. I'm going to have to tell the controller something's gone wrong. But we do that gracefully, and we can say, hang on, we've got a problem here. Some of the system's gone wrong. We don't crash, we don't fall over, okay? You remember those little proofs that Rod showed up, that little snippet of proof, okay? 250,000 lines of code generates 150,000 of those little proofs, okay? So the good news is, as Rod said, we don't do them by hand. That would be dull. 99% of them are just discharged by the theorem provers automatically, and leaving a smaller number to go look at. Okay, 153,000 proofs. That sounds quite a lot. Rod was talking about the speed as well. How long does that take? Okay, well, actually, if we start from scratch from a completely bare system, we can reprove the entire system in about 2 hours. Okay, so you're in overnight category there. Okay, I know some of my team would like to consider 2 hours a lunch break category. You're not. You're in overnight category there. However, a lot of those proofs turn out to have a lot of commonality, particularly in the subproofs, yeah? So actually, if you start caching the results as you go along, you can speed that up quite dramatically. So if you run it overnight for 2 hours and build a cache, actually, any of our developers can reprove the entire system in about 15 minutes, okay? And because it's modular, if you've just made a code change to one module, one piece of code, you can reprove it in a couple of seconds, literally a couple of seconds. We're into the category where your fingers aren't quite off the keyboard, as Rod was talking about earlier. As a result of that, this kind of proof, this kind of analysis activity is a pre-commit activity for all of our developers all of the time, okay? It's not something we do retrospectively. We do run it overnight as a retrospective, but it's belt and braces, right? Before any commit, the tooling runs and checks all of this kind of stuff, and the bugs or any of the issues that are found are fixed before the commit. Okay, Rod's going to talk a bit about the future and set you homework, right? Because if you don't leave doing something, it wasn't worth it.
Okay, so just one small idea for the future. Thank you, John. These tools, for the first couple of months of using tooling like this, it's really annoying because every line of code you write, the tool says, no, wrong. It's like having the worst code reviewer ever, the most pedantic professor check your code. And for those couple of months, it just kind of batters you. And you're like, oh, I've done it wrong again, another buffer overflow. It makes you humble. It makes you realize what a brilliant programmer you're not. And it's really important that you realize this. All of you inject somewhere between 20 to 100 defects per 1,000 lines of code in handwritten code in most programming languages. Nobody is good enough to handwrite safety critical code without some serious assistance and tooling. So don't think I'm a brilliant programmer, right? You're not. But that's okay, because nobody's that good, okay? So it's really, really important that we've adopted this idea called fumble programming at work, which is a bit of a laugh, but basically fumble means formal and humble. So it's using the F word, formal methods, shock horror, mathematics, but being humble about it. And now when the tool catches me out, I say, oh, thank God the tool's found a bug and I wouldn't have to find that by testing. Thank you, Mr. Theorem Prover, or whatever. The niche where this matters is growing. If you're building a system like it's an IoT thing and it's connected to an open network, you need to get pretty serious about correctness of your software. The number of bugs we're seeing in cars and any God knows what connected devices, bad news. And we can do this. Thank you, John, I'm there. So just do it. Yeah, JFDI stands for just do it with a silent F. So as I said, I'm going to set you homework, because if you go away from this conference and don't do anything, you're supposed to be inspired to do something. So inspiration number one is go have a play with the technology. As Neil said, all of this Spark technology, by the way, is freely licensed. It's all available under the GPL version 3. And there's a book. So go buy the book. If you're old-fashioned, read the book, or just go look online. Homework for everybody, read that book. It's brilliant. If you want to know how surgeons get it right, go read the Checklist Manifesto by Atul Gawande. It's awesome. It will persuade you not to go into hospital. Your boss should read this book. This is the best and shortest book about why correctness and quality matters in software, winning with software. This is Watts Humphrey, who's one of the great unsung heroes of software engineering from Carnegie Mellon, the Software Engineering Institute. With that, I will say thank you all for listening. Thank you for coming. I hope you have a great day. And Neil and I will allow John to field questions. Thank you very much indeed.
So all the sessions are being recorded, so you don't need to take notes, but please do wait for the mic to ask a question.
What was the helicopter bug?
What was the bug? There was a small HMI bug, okay, which drew without getting into it. The HMI it's kind of a basic ASCII display because it's designed to work in freezing temperatures in the Arctic and all that kind of stuff, and it draws some columns, right, before putting numbers in, and one of the columns wasn't quite drawn straight.
You mentioned concurrency, but avoided going into any details.
Should we answer that together? You do a bit, and then I'll do a bit.
Particularly for concurrency, we can support a very basic model of concurrency, which is suitable for building hard real-time embedded systems. There is a whole strand of research on something called schedulability analysis for real-time systems, where you say, well, given all these tasks and the way they communicate, am I going to meet my deadlines? Have I got enough CPU time available to actually do everything I need to do? And is this task going to be able to respond in 3 milliseconds to this request? There's a whole bunch of mathematical theory about how you do that. The thing to Google is the name of a town in North Yorkshire called Ravenscar. If you Google Ravenscar tasking or Ravenscar concurrency, you'll find that's the way we do it. But it's very, very simple. Yeah.
With these kinds of software systems, how do you start? Like, do you get given an emulated environment in which you can start developing these verification statements, or like you just do the customers generally give you those sorts of statements?
In terms of the requirements for the system, you mean?
Yeah.
It's a mix. Some of our customers give us pretty good requirements for the systems. To be honest, we work best when our customers, generally the best relationship is when the customers rock up and go, I have a problem, this is my problem, can you help? Yeah? And then we work with them from that problem statement onwards through to what a solution might look like and deliver it. Yeah? So the air traffic control one, for example, we genuinely started there with bits of cardboard cut out of cereal packets when they tried to explain what they wanted us to do. And we worked with them what that might be. We mocked up some prototypes that they could play with, and then built a hardened system that can work. So it goes from everything from there, but other times, customers do rock up and say, I know exactly what I want. I want a system that does this. Requirement 1, bang. Requirement 2, bang. Requirement 3, bang. Requirement 4, bang. And 7,849, bang, end. Yeah, so a variety.
Hi there. You've talked about building from the ADA subset up and building an entire stack of tools. Is it possible to easily incorporate stuff that's happening, say, in universities, like, from other programming traditions like Agda, Coq, that kind of thing? Or you sort of, are all these efforts kind of silos where nobody can reuse each other's stuff?
Technologically, we did a big reboot a couple of years ago where we went from a very closed proprietary technology to being much more open with the GPL licensing. Particularly in terms of theorem proving now, we actually build on top of an infrastructure called SMTlib, which is the sort of lingua franca of theorem proving that all the theorem provers talk. There's a language called SMT. So we actually, at the moment, use 3 different theorem provers, and we actually can interface out to some of the other popular proving systems like Coq and Isabel Hall, I believe. So we are open up. We're trying to open up as much as we can to take advantage of all those other technologies. So it's a lot more open than it used to be. And the team that do the research work with the people at INRIA in France and CEA in France and the CVC4 team at NYU and Stanford, who develop the theorem provers. We interact with those teams a lot actually these days and incorporate those techs. So it's opened up a lot from where it was 10 years ago.
Yeah, so a different talk I do, I've got like a timeline slide that shows the evolution of this technology, and there's something like 25 different academic university institutions that at some point have contributed some kind of research that's ended up in this tool chain. So when you look at it back, it's a great example of collaboration across countries, universities working together, and increasingly, as Rod said, commercial enterprises like Microsoft providing theorem checkers, which are an awful lot better than some of their other tools.
Yeah, hi there. So Cyber UK earlier in the year, NCSC, they were, say promoting is probably the right word, about the Rust programming language.
Yeah.
And I guess I was just wondering, is that something you're considering? Is Rust something that would work with this tool set?
Rust is interesting. It wouldn't work with this tool set per se, but the answer is, could you build something like Spark based on Rust? And I think the answer is possibly. Rust makes some very great steps forward in several levels. Obviously, the way Rust deals with pointers is very interesting and things, and the way it deals with something called traits is very interesting, and I think something we could learn from. I think Rust makes a number of, one substantial design error in Rust is that the primitive scalar types are basically the same as what they are in C and C++, and it exposes the machine. Integers are 32-bit or 16-bit. And this is a terrible, terrible missed opportunity in Rust. In Spark, we have types where you say the number of working engines is 0 through 4. And that's about the problem domain, not the machine. That opportunity has been missed in Rust. And it's a terrible loss because having the type system model the real world is what allows the theorem prover to work really, really well. Because if I didn't know that, the theorem prover wouldn't be able to decide anything useful about my program. So in a world where everything's a 32-bit signed integer, the theorem provers are crap. They don't perform well because there's not enough information in the program to prove anything useful. Like, can you prove if a computation will or won't overflow? Oh, it's really hard if all your numbers are signed 32-bit int. And Rust misses that. I think that's a problem. So it'll be interesting to see what happens with Rust. It'll be interesting to see if a really strong verification tool emerges for Rust. I don't see one yet on the market, but it would be a good thing if it did, probably.
It's certainly something the R&D team are keeping an eye on and looking. And we were at Cyber UK as well. I'm not sure it was quite as much as promoted, but they've certainly been talked about. Nobody's yet certified a security system in Rust.
I'm just going to have a look at his badge. Hang on. See where he's come from.
Nobody's yet certified a security system in Rust, but it's definitely something the R&D team are looking at and keeping an eye on. And there's as Rob says, possibilities for the future. It'll be interesting to see where it goes.
So for runtime performance, are you reliant on traditional compiler optimizations? And if so, how do you guarantee that the compiler itself isn't introducing bugs beyond the level of all your verification? I say this as somebody who works with an optimizer, so I know that it happens.
You can be guaranteed. Someone will say, what about cosmic radiation, right? Because what if a RAM chip flips? And someone will say, should I trust the compiler? We trust the compilers about the same as you do with any other language. But we have no undefined behavior. We have no dependence on unspecified behavior, and implementation-defined behavior is very carefully controlled. So actually what you find is that Spark programs are uncannily good at being optimized because they're correct and they don't have any undefined behavior in. The optimizers behave very, very well with Spark programs, which is really, really good. So the Skein program, I showed you the Skein code, the Spark version of Skein compiles with GCC at all optimization levels, and at some of those optimization levels, it outperforms the C code. Right? We get bare metal performance that is sometimes even better than C out of Spark. Because the code is so good, the optimizer can make better assumptions about the fact there are no function side effects, no aliasing, there's no undefined variables, blah, blah, blah. The optimizers actually do a better job on Spark code than we do with C. And the main big compiler for Spark in the world, by the way, is GCC, which might surprise you, but it turns out the GCC Ada compiler is a work of genius and is very, very strong and very capable. So it's the same optimizer as you'd get with any other build of GCC.
So the flip side of that, we completely agree with everything Rod said, but we've also had activities where we've taken the source code, okay, and we've taken the object code that's come out of the compiler, and we've written tools and manually checked that they're the same, because there are platforms where the compiler's not as common, not as used, not as trusted, and we've had to go, actually, I don't trust it as far as I can throw it. I am going to have to check the object code looks like what the source code should look like. Yeah. It's not something I'd recommend unless you're trying to get off to sleep.
1% of 153,000 is 1,500.
Oh, it's still a lot, yeah.
That seems to me to be quite a large number. And if you really get the speed of re-verifying, presumably those aren't re-verified by hand. Could you explain how that's handled?
No, I could spend a whole talk explaining how that's, yeah. So that 99% are the ones where the theorem prover just goes, yes, I've got enough, I know about it, bang, okay? The other 1%, and you're right, 1% of a big number is a big number, and it matters, is where we've had to tell it some extra information, yeah? So potentially there are some things, I can't think of a really good example off the top of my head, but potentially you can tag the verification condition, say, actually, there's a piece of domain information which is true and holds here, yeah? And then the theorem prover can go, well, I know these facts, and I know this new tagged fact, now I can prove it, whoopie-doo. So what you do is you look at them once, yeah? Provide that little extra piece of information, and then in future run-throughs, the 2 hours, the whatever, they all 100% go through, yeah?
And will those get exposed in the contracts?
Yeah, so there's a number of ways you can do it. You can either do it at the source code level with the contract and actually write in the contract in the source code. By the way, when we get here, we know because this has happened that this statement is true, and then the tools will check that statement is true, and the theorem prover will know it. Or you can do it at theorem prover level and say, actually, yes, the clock will overflow when the clock gets to this. However, that will be 40 million years in the future. We're not going to worry about it. Yeah.
Fantastic. Right. So we thank you for a fantastic talk, awesome questions. I think you've got about 7 minutes to get to the next talk if you're not staying here. But a big round of applause for Rod and Neil. Thank you.
Thank you.